All right, guys. So you just finished watching the first video, and hopefully, we're going to get a reinforcement here. You see the first video. We're going to go over the worksheet that you have here that goes through all the steps of respiration, and then finally, we'll watch one more video that'll, again, reinforce this. All right. So I'm not going to be writing the answers to here, so you're going to have to listen up, but you should be able to get all the answers. So this first diagram here, and I'm sorry if it's not focusing too clearly, but you should have this diagram here. This is showing ATP, the hydrolysis of ATP, or the breakdown of ATP when that one phosphate is broken off. But the question asks, this diagram shows a breakdown, but explain where the energy comes from to form ATP. So like if we were going in the opposite direction, we were putting that phosphate back on. Where does that energy come from? Well, it comes from cellular respiration, and that's what we're going into here. Okay, so that's your first question there. Now you'll notice the worksheet that I gave you that's online doesn't have this extra line in here, and I'll explain why that's on there. It really should be on there. And it doesn't have some of these numbers in here. So if you want to add to your diagram or something, that's fine. If you don't, that's fine too. Okay, but this is an overview of respiration, and we see the 4 steps. Most science books will say there are 3 steps to respiration. That's glycolysis, the citric acid cycle or the Krebs cycle, and then oxidative phosphorylation, which includes electron transport and chemiosmosis. I like to mention this 4th step, this pyruvate oxidation, or sometimes called the formation of pyruvic acid, because there are some of these NADHs that come out of there. We just call them the NADs, okay? So we're going to start with glycolysis, and we're going to see by the end of glycolysis, this is kind of like ruining the ending to the more complex version. But by the end of glycolysis, we're going to get 2 ATPs. Notice that this also takes place out in the cytoplasm. Also, by the end of glycolysis, after that glucose is converted to pyruvate, that pyruvate will move on, but we also get these 2 NADs, NADHs. These are those electron carriers that they mentioned, and they're going to carry them over to the final step. So, glycolysis happens in the cytoplasm, or the cytosol, produces 2 ATPs. You'll see where 2 are invested and 4 are produced, so we get a net total of 2. And then 2 NADs move on. Second step, pyruvate oxidation, or formation of pyruvic acid. 2 NADs are going to be produced here as well. No ATPs, but notice that this goes on into the mitochondria. That pyruvate goes on and gets converted to acetyl coenzyme A. Acetyl coenzyme A will enter into the citric acid cycle or the Krebs cycle. You can call it either one. Okay, and during this whole cycle, which will look much more complex on the next thing, we're only going to get 2 ATPs out, but we're going to certainly churn out a lot of NADs and these FADs, 6 NADs and 2 FADs. Okay, they're also going to go to oxidative phosphorylation at the end. And then finally, this last step, which includes electron transport and chemiosmosis, produces approximately 32 ATPs. That's a debatable number. Like science books will say it's anywhere from 30 to, or 28, I think, to 38 almost. 32 seems to be a very explainable number, and we'll see how that goes later. Okay, so no questions on this overview. So let's get right into the first stage of cellular respiration, which on this side of the page is a very complex form. I give this to you because if you go on into college biology or college chemistry, you might need to know these detailed steps of glycolysis. But to be honest, for right now, I don't care that you know these detailed steps and all the intermediate forms of it. It's just not really that important. But why are we even doing this? Why are we even going through all these steps? This is a big time metabolic pathway, and there's thousands of metabolic pathways in living organisms. And it's good to learn one. I mean, it's kind of like a domino effect. This affects that, which affects this. And it's kind of good to learn one of these because, like I said, research in the future, you might be focusing on a certain metabolic pathway, and you might be doing research on how to control the steps of that, or, figure out what enzymes control it. So I like to teach this. It's a little something different than usual in biology, and it is something very important to learn. Okay, so we have a couple of questions here, and hopefully we're going to answer them here. All right, so this is glycolysis. We're in the mitochondria, okay? Now, we always talk about glycolysis having an energy investment phase and then an energy payoff phase. The energy investment phase, okay, is where we put 2 ATPs in. So we're kind of like down 2 ATPs. It's like kind of like spending $2 to make a little bit of money. And in that phase, we're going to split that glucose into two compounds, okay? But that's part of the investment. We got to do that to start breaking that glucose down, getting that energy out. Well, in the second part, and sometimes we call that energy that's used there, we call it activation energy. Activation energy. Okay. And that activation energy is going to start this whole process, okay? Then we go into the energy payoff. 4 ATPs will come out. So we know that we're going to get a grand total, a net total, I should say. If we spend 2 and make 4, we only really get 2 ATPs out. But we also get those NADs. Those are the electron carriers, okay? And they're going to go to that last step. So if you summed up glycolysis, it takes glucose, it invests 2 ATPs, which splits that glucose, pays off 4 ATPs, giving you a total of 2, but also sends out NADs that will go on to the last phase, and you get 2 pyruvate molecules because that was split into 2. Okay, so if we look at these one more time, the activation energy is that investment phase. That's at 2. What was the starting molecule? Obviously, glucose. What was the end molecule? 2 pyruvic acids or pyruvates. You can call it either one. What else was made that will move on to another phase? That's the NADs. Okay, they are going to move on later. How many carbons were lost? Well, no carbon dioxide was lost here, so there were no carbons lost. So glucose being a 6-carbon compound, pyruvates are a 3-carbon compound apiece. So you got 2 times 3, which adds up to a 6. So no carbons were lost. Where does glycolysis take place? This is right into the mitochondria. Glycolysis. Sorry, this is in the cytosol. Mistake there. Cytoplasm, cytosol, same thing. It takes place right outside the mitochondria. And what was the total ATP gain? Well, we invested 2, made 4, so the total was 2. All right, so now we move on to the next phase. Okay, and the next phase is what I call that conversion of pyruvate. So here's a pyruvate molecule, and it's showing the 3 carbons. Okay, and you saw that in the video, those 3 carbons like enter the mitochondria. So they go through the little pores in the mitochondria membrane, and that's where it loses carbon dioxide right off. So that those pyruvates, and remember there's 2, so this happens twice. Okay, so 2 of those carbon dioxides come off, 1 from each pyruvate, and it sends it down to being this acetyl compound. Ignore the coenzyme A for a moment. Acetyl has 2 carbons to it. But what else happens during that? Well, we have this coenzyme A that attaches to this acetyl group just temporarily, so that there go those electron carriers again. The NADs can go through and collect electrons and send them down to that last step. So all in all, this step, remember, it happens twice because you have 2 pyruvate molecules. So from 1 glucose, you had 2 pyruvate molecules. So therefore, we get NADs, 2 of them because it happens twice, 2 carbon dioxides because it happens twice, and acetyl coenzymes, 2 of them are going into the next phase. So what was made per pyruvate? What was made? Well, no ATPs, that's for sure, but definitely per pyruvate, 1 carbon dioxide. But then the next question says what was made per glucose molecule. Remember, 2 pyruvates came. Then it would be 2 carbon dioxides. And you could also add to both of them what was made per pyruvate, also a NAD, 1, but 2 NADs down here, and 1 acetyl coenzyme A up here, but 2 down here. So I'm asking you from 1 versus from the glucose molecule, which made 2. What was the starting molecule? Pyruvate. What was the end molecule? Acetyl coenzyme A. How many carbons were lost? Only 1 from each pyruvate. You might want to state that. How many carbons were lost? 1 from each pyruvate. And where does this process take place? Well, we're in the mitochondria. Okay, so now let's go deeper into the mitochondria. Now we're going into actually the matrix of the mitochondria. And here are those acetyl coenzyme A's right here. And they are entering in, but how they're entering in, notice there's 2 carbons to them. They hook up with this 4-carbon oxaloacetate, right? Acetyl plus oxaloacetate, or 2 plus 4, makes a 6-carbon citrate group. 1, 2, 3, 4, 5, 6. Citrate is also citric acid, okay? So that is what we call like the first one where we see this connection made. There goes some NADs, and look, there goes some carbon dioxide. So if you let go of 1 carbon dioxide, that's going to reduce that number down to 5. And we have this alpha ketoglutarate or alpha ketogluteric acid, okay? Another carbon dioxide is going to leave, more NADs are going to leave, but also we get a little ATP. Okay, now remember, we're only following 1 acetyl group going through this. So we had 1 NAD go through, 2 NADs go through, we had 2 losses of carbon dioxide and 1 ATP produced. Then it comes around again, and now because that has reduced by carbon dioxide, the 5 came down to 4, and now we have succinate. Okay, succinate, here goes another electron carrier called a fad. It's not as powerful as the NADs, but it still is going to carry electrons to the final step. And notice no carbon dioxide is lost, no ATP is produced, but so this is why we remain at 4 carbons, and we stay at 4 carbons when 1 more NAD goes through. So if we count up our NADs, 1, 2, 3, times 2, remember this is going around twice, and our carbon dioxide's 1, 2, times 2, so that makes 4, and 1 NAD times 2, we can see that in the citric acid cycle, we got 1, 2, 3 times 2, 6 NADs, 1 times 2, 2 fads, and 2 times 2, 2 carbon dioxides, and 1 times 2 ATPs. All right, so let's sum up this, and we're going to sum up answering these questions, and then we'll probably end this little video of mine, go on to one more video of Mrs. Horner's, and then you'll watch one more final video. So what was made per 1 turn of the cycle that goes on to oxidative phosphorylation? That's the last cycle. Well, 1 turn gave you 1, 2, 3 NADs and 1 fad, 1 turn. How many carbon dioxide molecules were made per glucose molecule? So again, remember this has to happen twice because there were 2 acetyls coming from that original glucose. So 2 turns to, that would be 4 molecules, okay? What was the entering molecule and what did it become? Entered as acetyl. What did it become? Citrate when it attached to oxaloacetate. All right. What was the end molecule that would cycle around again? That's that oxaloacetate. Okay. How many carbons were lost in 1 turn? 1, 2 carbons were lost in 1 turn. Where does this process take place? It takes place in the mitochondria, deep in the mitochondria called the matrix. And how many ATP molecules were made total from 1 glucose? So that's where it goes around twice. So there's 1, but goes around twice. So that's 2 ATP molecules. Okay. Now I'm going to end this video because I'm going to start the last video, which is going to be the oxidative phosphorylation.